Welcome back. In the last video, we looked at proving that this set here was linearly dependent. And we got into a tiny bit of trouble because we started with a vector that wasn't a linear combination of the other three. And so we had to actually solve two different systems and start again with a new one. And so we would rather avoid having to pick one of the vectors to write as a linear combination of the other ones. You can imagine this being a big pain in huge sets. So when showing that a set S is linearly dependent, we want to avoid guessing which element of S can be written as a linear combination of the other elements of S. Similarly, when proving that S is linearly independent, we do not want to have to show that each of the vectors of S cannot be written as a linear combination of the other elements of S. Right? I don't want to have to prove that 5 different vectors are not written as the linear combination of the other 4. That would take way too much time. All right, so the following theorem gives us a criterion which is symmetric in the vectors of S and will make our work more straightforward. All right, so theorem 1.4.1, I'm going to assume that S is a finite set. Let's take this to be a subset of V. S is linearly dependent if and only if they are real numbers a1 through an, and then this is the point, not all 0, so that a1 v1 plus a2 v2 plus an vn is the 0 element in V. All right, so S is linearly dependent if and only if the only numbers a1 through an in R, so that a1 v1 plus a2 v2 plus an vn equals 0, are a1 equals a2 equals an equals 0. All right, so instead of trying to write one as a linear combination of the other, we put them all on the same side, and now we're asking how many solutions does a system have. If it has only the trivial solution, you're going to have a linearly independent set. If you have infinitely many solutions, so you have one that's not completely 0, you'll have a linearly dependent set. All right, so I want to prove that this is equivalent to the original definition. All right, so I'm going to prove 1, 2 follows just because dependent and independent, independent, if and only if, yeah, that works. All right, so assume that S is linearly dependent. I want to prove that this here is true. Then there's one of the VI's that can be written as a linear combination of the other elements of S. So I can write something like this. All right, so I'm really skipping VI because I'm not allowed to use it. All right, so there is some I for which this is true. So if I send VI to the other side, I'll get the 0 of V equals A1 V1, AI minus 1 VI minus 1. And then I'm going to insert minus 1 VI, and then I'll have the rest here. And so I do have a solution for something like this. And notice that this element here, the constant in front, is not 0. So this one is not 0. And so yes, we have a non-zero solution to, or a non-trivial solution to this equation. All right, so that's one direction. Then the second one, I'm going to assume that we do have this part, that we do have a solution that's non-zero, and from it, I want to prove that S is linearly dependent. So I want to write one of the vectors as a linear combination of the other ones. All right, so I'm assuming that I have the zero element of V written as a linear combination, and I'm told that one of them is not zero. So let's assume AI is not zero. So I have 0V equals A1 V1, and then I have my special one here. This one isn't zero, so I'm going to send it to the other side. I'll get minus AI VI, and then here on this side, I will no longer have any VIs. So I'm skipping VI. All right, but I don't want minus AI VI, I just want VI. So here I'm going to multiply by a real number, which exists because AI is not zero. And so I will get VI times 1. And so that's just VI by axiom 10. And then here I'm going to multiply it all by this number, and I'm going to be able to distribute and put it with the constants in front. So again, here we are using a lot of the axioms without mentioning them. All right, so here I'm going to get minus A1 AI V1 plus minus AI minus 1 AI VI minus 1 plus minus AI plus 1 AI VI plus 1, and so on. And so yes, VI is a linear combination of the other ones. Let me make a tiny bit more room, which is linearly dependent.